got a flashlight here. It's transparent so you can see what the problem is. There's no battery. So even when I turn it on, nothing happens. What I do have inside here is this coil of wire and this silver thing. It floats. What is it?
A magnet.
It's a magnet. All right. The instructions on the side say give this 90 short, fast shakes. So shake it as hard as you can and as fast as you can. And pass it to your sister when you're tired. Are you starting to see the blue light of the force at the top of the flashlight? Let's take a look. Check it out. It's on. Look at the ceiling. It is on like anything. So, take a look at electromagnetism principle number 1 from yesterday. Pause the video and see how you can figure out how we got a current in this flashlight without using any batteries, any sources of electric charge, any sources of voltage at all. Yesterday, you figured out that changing electric fields create magnetic fields. So if changing electric fields create magnetic fields, what else do you think is true? Consider principle of electromagnetism number 2. So, given that changing electric fields create magnetic fields, what else is true?
Changing magnetic fields creates electric fields.
How did we change this magnet? Did we cut it? Did we paint it? Did we make it bigger or smaller?
Wire.
Oh, the wire didn't change the magnet.
Didn't.
No. What change did the magnet undergo?
Moving.
It moved to change its location. There we go. Please notice that the right-hand rule is still in force. We moved the magnetic field and we changed it this way. And if we wanted to pick up that electric field as a current in the wire, we had to have a coil over here as per the right-hand rule and 2 strands of the coil going up here into the little circuit board controlling the light bulb. The market niche for this shake and bake flashlight is that of flashlights that don't need battery power, specifically road kits for people in the northern states, in Minnesota and Montana. If you're not in the biggest of big cities and your truck breaks down, it's going to be hours and hours before anybody named roadside assistance gets out to where you are. And if it's already 10 degrees below zero, you can't afford to be out there for 3 or 4 hours. You have to fix the truck yourself, and you have to keep warm. Everybody in the northern states knows perfectly well that you don't go anywhere in the winter, not only without a snow shovel in the trunk, but without a road kit, with blankets, with heating packs, and with a flashlight so you can see in the dark to fix your own truck. Now, of course, you put the flashlight in there in June, and your truck doesn't break down for another 2 years. So 2 years later, the following February, what's going to be true about the flashlight? Of course, the batteries are going to be dead. That lot of good that's going to do you as you sit there in the dark watching your digits turn to ice and fall off. So, roadside assistance kit flashlights are made with instructions that it says shake a certain number of times at a certain speed to get the light to go on. Now I ask you, who wants to sit there shaking a flashlight in one hand and fixing the truck with the other? The light would go over the place. You wouldn't be able to see under the hood what you're doing. So think of another way, another direction that you could move the magnet other than forward and backward, or like the flashlight that we have, squeezing it in and out with the magnet mounted on a spring, which I have used to see what's going on in difficult times. Let me tell you, although the light stays stable, your hand kind of gets tired after a while going boingy, 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 boingy. Press play when you're ready to check your guess. Several people suggested that you crank the magnet around in a circle as a way of changing the magnetic field. North to south, flip upside down, going round and round. We're not changing the magnetic field very much because we're moving it slowly, so you can try cranking a little bit faster, then a little faster still. Check out the current in the light bulb, on and off, and on and off, and on and off. Ladies and gentlemen, I think we have invented alternating current. Check it out. So, here's a diagram of what's going on. We've got wire, we've got electrons in the wire, and we've got the right-hand rule with a fairly straight magnetic field line coming this way here. And if we change the magnetic field, if we make it stronger, by moving it closer to the North Pole or make it away from the South Pole, notice that having the magnet here does absolutely nothing. It's the change that's the issue. The faster we change, the more of an electric field we have. Notice the difference in direction as north goes in and north goes out, as south goes in and south goes out. Faraday's law gives us several variables to play with, starting with how big this loop of wire is. We said that current will flow as per the right-hand rule, in or out, but we didn't say how much current would flow. Let's make the loop bigger and see how that changes what we can see. Let's make more loops in the coil of wire. Well, that certainly seems to have made a difference. And fewer loops. And a smaller area. I think we've got a pretty good model. Okay, you can crank a little faster. You can crank till the light comes on. So here is our generator for alternating current. Changing magnetic fields create electric fields, and the electric fields create currents if you're in the correct orientation for the right-hand rule. Now we're going to try something fun with these genicons. Instead of hooking the leads to the light bulb, we're going to take the genicon and we're going to hook the leads to another genicon. So you hold this, and you keep cranking, and you can crank as fast as you like. Go on. Go next, as fast as you want. Way cool!
How did you do that?
All right, now you stop cranking, and you start. Ah! Go the other way. Now you go the other way. Are they turning the same way or are they turning different ways? Interesting. Hypothesize as to why they're turning different ways if they're identical pieces of equipment. Pause, press play to see what they can do. What could you do to change the way the electric current flows? Give it a try. See if that's what controls the direction of the brand new word, motor. One, and two. Okay, give it a try. Which way are they turning now?
Same way.
Yay! Go as fast as you can. Ah! Now,
We're at the third degree of freedom.
let's try one for Mommy. All right. Take it away, Shoshana. Go the other way.
Yours is going the opposite way as ours.
How fast are ours turning, yours and mine?
Slower than hers.
Okay, now let me take a turn.
Slower than yours.
Aha. Now, which way is yours going?
The opposite way as yours.
Okay, start cranking. Hey, how come Shawnee's isn't moving at all?
Because it neutralizes it.
Okay, now if you crank in the same direction as mine instead of the opposite direction.
No, I have to change in the opposite direction for it to work.
Or we could add the voltages and Shawnee's could go crazy.
Can you do that?
One more time. We have invented so many things in one device, it's hard to keep track of them all. We've invented a generator, a machine that you can crank and makes electricity for you even when you don't have a battery. We've invented alternating current, and we've also invented a motor. Notice that when we plugged the two genicons into each other and turned one of them, that is, we gave it electricity, the other one spun. A motor is a machine that when you plug it in, it spins. Your official definition for a generator is a machine that converts kinetic energy to electric potential energy. This is different than a battery, which converts chemical potential energy to electric potential energy. The generator will have the power to revolutionize the civilized world and kick off the Industrial Revolution because kinetic energy is a lot easier to come by than electric potential energy. Let's use what we learned in Faraday's law. Make the loop bigger, make as many loops as possible. Now, let's take a look at what happens. We turn the wheel, or better still, we get something else to turn it for us. The magnet spins, changing the magnetic field. The compass needle will show you how the magnetic field is changing. Look for the right-hand rule in action. When the field is perpendicular to the coil, with south facing one way, the current flows one way. When the field is perpendicular to the coil, with north facing that way, the current flows the other way. When the magnet is aligned so that the field is parallel to the coil, there's nothing doing by the right-hand rule, and that means no current flows at all. Give more water, or in the case of a steam engine, more steam, it'll turn the wheel more quickly, the magnetic field will change more quickly, and we'll get a much bigger current. Pretty cool, huh? Here's how it works. A generator converts the kinetic energy into electric potential energy by looking at the alignment of magnetic fields. Right-hand rule tells you which way the electric field is. Turn your coil 90 degrees so that current will flow. Notice that it's the turning that makes the current as much as the orientation, so there's no point in setting it up the right way to begin with. Otherwise, you'd just have to turn it to get the magnetic field changing, and then you'd be oriented the wrong way. Keep turning so the magnetic field will keep changing. Current won't flow, but that's okay. It will alternate. Current will flow in the opposite direction, and then it'll go back to zero. Here is an HC generator. Turn it, and a current will be induced. A motor uses the same setup as a generator. It converts the electric potential energy from being plugged in into kinetic energy. The only difference is that where a generator has a wheel to be turned by some helpful physicist, alternatively a jet of steam or a wheel of water, the motor plugs in. It's got to plug into an AC source by definition. You'll see why. There are two magnetic fields in this problem. The permanent magnet generates one magnetic field, and the current in the coil has to be set up the right way, and the right way is to generate a misaligned magnetic field, a magnetic field that's pointing the other way. These are aligned south to south and north to north. That is repulsion. That is, the coil is repelled by the external magnetic field, and if you simply let it go, it will spin, trying to align itself with the external magnetic field. Now it's happy. 180 degrees later, that coil has flipped over, and here it will stay. Your motor has turned 1/2 a turn and is now going to stall. You don't want it to stall. You want it to keep turning. And this is where the alternating current comes in. And this is why Westinghouse won the Battle of the Currents at the Great Chicago World's Fair in 1893, right here in Jackson Park. Westinghouse pointed out that the AC will change the direction for you, and that means the coil is going to keep turning. Motors, by definition, have to have an alternating current so that they don't stall, discover their magnetic fields are aligned, and sit there very happily. Plug a coil into a changing current, misalign it with an external magnetic field, and it will spin. Repeat, and you can hook a fan to your motor to cool your computer and your electronics components. You can hook a belt to the motor to power any kind of machine, and you can go nuts. Review. Why alternating current? Well, you can't change direction with DC. It doesn't work that way. DC is scheduled to go 180 degrees and then stall. A motor needs a changing current by definition, and this means a battery-powered motor ought to be a contradiction in terms. Fortunately, even in Edison's time, some clever wonk had invented a commutator. A commutator is a way to switch the direction of the current manually, preferably not by you sticking your hands in there and switching the red and the black wires every time. The 19th century engineers were working with the question of how we can change the direction of the current. We need something that's going to switch every 180 degrees. You can see the commutator has two circles. They're color-coded here, red and blue. They're made of conducting metal, and they are connected to, they're called brushes, but in our lab you'll see they're actually made of metal. They're metal clips. And as the circle rotates 180 degrees, notice the gap here that's usually filled with air if it's crosscut, or better still an insulator. It switches whether the top brush is on the red, on the high voltage, or on the blue, that's low voltage. Every 180 degrees, high and low voltage switch positions. The insulator makes sure that we still have current going around the loop and not in one big blob. Coil rotates 180 degrees, trying to align with the magnetic field. You'll have to give this a push to get it started, and you'll have to make sure that those commutator brushes are actually touching the connecting circle, but it will spin. Repeat. Once you've given it a push, your motor will spin. For this reason, you can have battery-powered motors in handheld devices that you have at home. If you're too cheap to buy a commutator or build one yourself, or your budget doesn't allow for that kind of finicky material, there's another kind of DC motor you can make, a really efficient and cheap one. And that is, when you're making your coil of wire, only scrape off half the insulation on the ends. Have each end have an insulated side where current will not flow, and an uninsulated side where current will flow. This motor uses inertia to spin. An object that starts spinning will keep spinning unless an outside force interferes by conservation of angular momentum. Your coil has to be an absolutely perfect circle, perfectly symmetric on all sides so that the force of gravity doesn't interfere. Every time your magnetic fields align, as the coil rotates 180 degrees, you will get to the insulated side of the wire. The current will shut off. There will be no second magnetic field to align with the first, and conservation of angular momentum will keep the coil rotating as it was rotating before in beautiful dynamic equilibrium until it flips over to the other side where the current goes on again. You discover those magnetic fields were misaligned, which is why you started spinning in the first place, and you get another boost of energy to keep spinning.